Okay. All right. Now, let's see. Well, time is certainly not a concern at this point. Any homework questions?
It's not a question, but I want to say that I have probably done like 2 or 3 more parts of number 2.
Woo!
I'm making progress.
Okay, cool. That's something. All right. Let's see. So, okay, so problems 1, 2, and 3, that's homework 1, and then 4 or 5 are homework 2, and then problems 6 and 7 are homework 3. Honestly, I'd be stunned if anyone has even started homework 3. But
yeah, I'm working on problem 5 now, so I'm close to homework 3 at least.
Okay, all right, that's something. So, well, yeah, there's still a decent amount of time left. Okay, so, well, thankfully the semester is starting to dwindle. Okay, so I want to, I guess, give a first bits of information about the final. So it is an oral final, and some of you may not have experienced that with me before. So my apologies if that sounds scary. So, but the way it works is that, well, I guess now it'll be conducted over Teams, or it can be done in person because some students do meet with me that way. It doesn't matter to me. But we just set a time, and so I'll just ask you questions about whatever aspects of this course material, and where I will look to for inspiration as to for questions will be the notes. So someone who understands what's in the notes well will be in good shape. Now, I will go through the notes and point out, I'll try to narrow it down to some degree as to what you should look at, because there's like 50-something pages of notes altogether. Well, as an example, certainly the chapter material on finite difference and spectral methods are of interest. And it's, I try not to get into the, too much into details. And as far as there may be times where I have you work out something on the board where I would steer you through it. But, I'm not really going to get into the code, the coding aspects. It's more like, for example, things I'd like to ask questions about are concepts such as consistency fidelity conversions. Also, why choose one method over another? What are advantages or disadvantages of certain approaches? When is a good situation to use a spectral method? Fourier versus Chebyshev, things like that. Okay, so maybe just giving you some of the questions, but but just to give you an idea. Once I look for the notes, because it's been a couple of years since I've done this, I will I'll see what additional info I can give. So as far as the timing, and the semester ends December 13th. Is that right? Yeah, that's when grades are due. So preferably sometime during finals week, and my schedule's quite flexible then. And if you want to get out of the way earlier, you can. So it's up to each of you individually to contact me and let me know of your preference. Yes.
So it's not all not all of it is us responding verbally. Some of it is writing things out.
It just occurred to me that is historically how I've done it. But again, I haven't done too many of these virtually.
Oh yeah.
Yeah, that does complicate matters a bit. Damn. Okay. Well. Also, yeah, because last time I taught this class, that was pre-COVID. Shoot. Okay. I mean, I didn't feel comfortable saying like, oh, well, in that case, then you have to come to my office and we do it that way. Here's a couple other options I can give. One is because there's more space conducted in one of these rooms. Another option is, I mean, I do like the idea of having board access of some kind. Whether it's like, well, okay, as an example, your office in a zone, is there a whiteboard? Oh, there's not.
No.
Damn. Okay.
But there are whiteboards in the center.
Right. So for instance, if you set up someplace with your computer to connect to me on Teams, where there is a board.
Oh yeah.
Yeah, we could do it that way.
Gotcha.
So
yeah.
Yeah, I want to try to recreate as much as possible how I've done this in the past.
Okay.
Yeah.
I just wasn't sure.
Yeah.
Dr. Lambers,
Yes.
if you wanted to do it virtually and you had like the option to write on your screen or tablet, would that be okay?
Yeah, that works too.
Okay.
Yeah, I mean, I know that technology is easier for some people to work with than others, but yeah, I will take that. Yeah, and you know, or if you already meet with me in my office for research, then you can just do that too. So up to each of you as to how you want to handle it. Okay, so that's something where when you let me know about the timing, then you can let me know about the delivery. All right. Okay. Yeah. Well, I'm glad that was brought up because I just wasn't even thinking about it. Okay.
I've just gotten very used to writing on my laptop, if you haven't noticed when I take notes in class.
Oh, yeah, certainly. Okay. Oh, and Caitlin, is that something yet, since you don't have the in-person option? um, is that something you can make work in one way or another, or?
Yeah, they gave us those little Wacom tablets whenever we were all teaching from home, so I should be able to do that probably.
Okay, all right, that works too. So, yeah, I have no familiarity with how those work, but yeah, so I guess you can show me. Okay. All right. Any other questions about this or homework?
Do we get bonus points if we do it virtually with a cat in the background?
Well, I know what Dr. Schroeder would say. Is that he would say no because not everyone has a cat.
I mean, we can make it universal to a pet in general. I think everyone except for Samson has a pet, but we can give him one to borrow.
Okay. Well, I could have spent a shift the grades up. Okay. Interesting idea. In some of my lower level classes, I used to give bonus points for particularly creative doodling on tests. So. Okay. All right. Any more mathematical questions than that? Okay. All right. Well, since this is sort of a little kind of day, and I'm sure you can relate, the only thing I have planned to cover is Runge-Kutta Methods. So I'm just going to go through that part of the notes, and then we're going to call it a day. Yeah. Okay. Appreciate the enthusiasm. Because that is how I feel about the idea too. Okay. Now, all right. Because last time I showed you the very simplest time-stepping methods, implicit Euler and explicit Euler, and showing that explicit Euler converges. But both methods are only first order accurate. So the error is proportional to delta t. So here we're going to look at some higher order methods. Now the thing is, if you look at the idea behind explicit Euler and what causes it to be first order accurate, you have y of tn plus 1. And this is Taylor expansion. Tn plus delta t f of tn y of tn. And keep in mind, this is our ODE that we're solving. So this right here, that is y prime for the next term in the Taylor series. And we have plus 1/2 delta t squared y double prime at an unknown point. And we just cut off a Taylor series there. And I mean, we don't know what it is, so we can't include it in our method. So then we end up with the actual method. Okay. And this term leads to the error term. Okay. Now, so in fact, this is equal to delta t times the local truncation error. All right. So, and that's why the local truncation error is order delta t, is first order accurate. So one might think the simplest way to get higher order accuracy is just to keep going in the Taylor expansion. So you could do yn plus 1 equals yn plus, so it starts out the same way. And then I'll include the next term. So 1/2 delta t squared times the derivative with respect to t of f of yn, there's a tn yn. Because this whole thing is y double prime. And then your error would be order delta, your local truncation error would be order delta t squared. So, but the problem with an approach like this is you have to approximate the derivative. of f. And it's actually worse than you might think, because the derivative with respect to t of f of t y of t, because y is a function of t, that would be equal to partial of f with respect to t plus partial of f with respect to y times dy dt, which would be f again. So you'd have to compute all this. So you need partial derivatives of f with respect to t and with respect to y. And if you're not able to evaluate f at just any old point, you have to use finite differences, so that introduces error also. So it just gets really tedious. And also, what if f is not very smooth? The accuracy of this approach would depend on higher order derivatives of f. What if those don't exist? So we want to try to find a better way of achieving higher order accuracy that does not require actually computing derivatives of f, because we don't actually need to do that. All right. And this is how Runge-Kutta methods come about. Okay. So what I'll do is I'll give you the general form of a Runge-Kutta method, and then show you certain specific ones. Okay. So the general Runge-Kutta or RK method has this form where yn plus 1 is equal to yn. Now, I'm going to be lazy and write these without vector symbols, but a Runge-Kutta method can be used for a single ODE or a system of ODEs. All works exactly the same. So you can think of y as being a scalar or a vector. Doesn't really affect the form of the method. Okay, plus delta t and a sum of linear combination Okay. Now, so then I have to describe, so these are just coefficients that help define the method. And then I have to tell you what these kj's are. So each kj is equal to the f, your time derivative, evaluated at selected t and y values. So tn plus some constant, so some multiple of delta t. And then second argument is a y value, so that's always equal to yn plus delta t times the sum. You need to be careful with my notation here. I a j I. I don't like this notation. Okay, sorry. I need to change my choice of letters here. So aij kj. All right. So what we have here is a kind of like a matrix vector product. Okay.
So now in the first equation of those i's.
Oh, here? Wait.
Yeah.
No, this is fine the way it is. Now, so here we take all the k's and put them in here, where each k is defined this way.
Right, I was just confused because here it's ki.
Right. Okay, these letters don't have to be the same though.
Okay.
Yeah, so for example, if I let S be the total number of terms we have in here, then this is the definition of ki for I equal S.
Okay, I see now.
Yeah. Yeah, and I was going to do it like you thought, except I want JI didn't sit well with me. Yeah. All right. So what happens is, in implementing a Runge-Kutta method, you evaluate the k's first. Once you have the k's, then you create this linear combination, and that's when you get yn plus 1 from yn. All right. Okay. Now, you notice there's a lot of coefficients here. We have a's, b's, and c's. And this leads to a particularly compact way of describing a Runge-Kutta method. Tableau form, where what you do is, here we have Aij, that defines a matrix. So a matrix A goes in this part of a tableau, and then these coefficients, the multiples of delta t that are added to Tn, is a column vector that goes over here. And then these coefficients, the b's, form a row vector that I put down there, B transpose. So if I were to give you the tableau, the A, B, and C, then you'd be able to write down or implement in MATLAB the Runge-Kutta method that goes with that tableau. So what I'm going to do is I'm going to describe certain Runge-Kutta methods in this form and the tableau, so you can see how to go back and forth. Yeah. All right. One thing to keep in mind is that if you look at each row, those elements of A in that row, oh wait. I think there's a mistake in the notes here. Yeah. Okay. Yes. If I take the sum of entries in a particular row, okay, so I is fixed. Oh, wait. Nope, sorry, the notes are correct. Thank God. Okay. If I add up all the elements in a row, so I is fixed, J is varying, that has to equal the corresponding element to C. So for a valid Runge-Kutta method, the vector C has to consist of a row sums of A. All right. Now, also, the RK method is explicit if and only if the matrix A is strictly lower triangular. meaning at aij equals 0 if I is less than or equal to j. So in other words, if you want an explicit method, you can't have any non-zero entries on the diagonal even. Okay. And we're going to see mostly explicit methods, but I'm going to have some implicit methods too. All right. So I realize it's kind of murky, but I'm about to show you some examples, and then you'll see how these methods can be represented both ways. Okay. It turns out that methods we've already seen, explicit Euler, implicit Euler, are technically Runge-Kutta methods. They're just very simple ones. They're only first order accurate. So explicit Euler, which as you know is y plus 1 equals yn plus delta t f of tn yn. So its tableau is okay. So we have because there's only one term here, so the number of terms s is equal to 1. So your matrix A is just a number, and it's 0. And the reason why is we're only evaluating f at tn and yn. So that means all the entries of C are 0, all the entries of A are 0. And because C has to have a row sums of A, C is also 0. And then we have a 1 down here for this coefficient. So you can think of this as K1 is f of tn yn. So then yn plus 1 is yn plus delta t K1. So to write it in a form that is consistent with this is how it would look. And that's where you can see what A, B, and C are. Everything's 0 except for this coefficient of K1 is 1. Right. So questions about our first tableau before looking at another. Okay. Implicit Euler also technically a Runge-Kutta method. Now we know implicit Euler in this form, yn plus 1 is yn plus delta t f of tn plus 1, yn plus 1. But I need to rewrite that in a way that fits our Runge-Kutta notation. So instead, I'll write yn plus 1 is equal to yn plus delta t K1, which is the same as in explicit Euler. But now I need to define K1 differently. F of tn plus 1, but that's the same as tn plus delta t. So what that means is we have a C1 is equal to 1 here. And what's the argument I put here? Well, this is supposed to be yn plus 1. But yn plus 1 doesn't fit this framework at all. What we put here is supposed to be yn plus a combination of the k's. Fortunately, we can do that. We actually do have yn plus 1 in that form. It's right here. So I can say yn plus delta t K1, which is yn plus 1 from right here. It may seem kind of weird, but it works. And here's the tableau. We still have the same 1 down below, or a multiple of K1. And then for your C, we have plus delta T. So we have a coefficient of 1 here for C1. And then over here, we have yn plus delta T K1. So the coefficient of K1 is equal to 1. So we have a 1 here also. So the tableau is all 1s. So if a matrix is 1 by 1 matrix, since it's non-zero, or it has a non-zero diagonal entry, the only entry it has, it's an implicit method. All right. Okay, questions about B's before I go into other ones? So whenever you need to define an implicit method, you use this form of yn plus 1 to figure out what your A coefficient should be. Right. Okay. You look at how many more Runge-Kutta methods I'm supposed to look at. 1, 2, 3, 4. Okay. Well, can't forget to take a picture of this. Okay, here's a oral final question for you. If I show you a Runge-Kutta method in either this form or this form, go your way. Can you convert notation? Actually, I haven't asked a question like that before, but it seems like fun.
This final's making more sense now that we talk, because in my head, I thought it was completely oral. Like, only you spoke, only I spoke, and there was no, like, writing. So this makes more sense.
Okay, so sometimes it has been like that.
Mm-hmm.
I hope it does not cause undue stress.
No, this makes more sense, because I was like, man, how is he gonna ask all these questions without even, like, having any math to look at?
Oh, I see. Yeah, okay, because it really does depend on the question. For example, if I'm going to ask you how, what's the relationship between consistency, stability, and convergence, you can just spit that out.
Yeah.
But for something like this, yeah, yeah. So, okay, well, I'm glad that got cleared up for you. Okay. Okay, I want to switch to the other board, or half of the board. Okay. Now, what I've shown you so far is two closely related methods, one explicit, one implicit. Now I'm going to do that again with what's called a midpoint method. Okay, so first is the explicit midpoint method, and then implicit. Yeah. Well, actually, it's probably best to write the implicit midpoint first. Well, let's take a look. Yeah, it's actually a simpler method of the two. So, because we only need a K1, and the idea is our K1 is evaluation of F at time Tn plus a half step. So Tn plus 1/2 delta T. And then corresponding to that, we want an approximation at y, instead of yn or yn plus 1, it'd be like yn plus a half. And the way that would go is yn plus 1/2 delta T K1. So notice that K1, like in implicit Euler, depends on itself. So what you'd actually have to do is use some iteration to compute K1, so that this equation is satisfied. To the K1 appearing here and here. Like you might think of an initial guess for K1. Plug it in over here, compute the output value, and then substitute back in. Successive substitution, also known as fixed point iteration. Be one good way to compute that. Okay. Now, this is supposed to be an approximation of yn plus a half. Okay. To go with Tn plus a half that we have right here. And you can kind of see why, because we're starting at yn, we're taking half a time step, 1/2 delta T, and then what's the appropriate slope? K1, which is a value of F at this time. So really what this is an approximation of yn plus a half using implicit Euler. Because what does implicit Euler do? It uses the value of F at the point you're trying to compute the solution at, which in this case is Tn plus a half. All right. Once you have K1, then you have yn plus 1 is yn plus delta T K1. Notice that's the same formula as in implicit Euler. It's actually, yeah, all three methods so far have the same formula for yn plus 1 in terms of yn and K1. It's the K1 that's different. All right. Questions about this one? I know it's kind of weird. Now, before we get to the tableau for this one, let's do implicit midpoint. So we want to achieve the same idea where we get the slope at time Tn plus a half, yn plus a half, but without having to do an implicit method. So that takes a little bit more work. So explicit midpoint, what we do is we let K1 equal F at Tn, yn, just like in explicit Euler. And then K2 is F Tn plus 1/2 delta T. And then yn plus 1/2 delta T K1. Notice that K2 has the same formula as K1 in the implicit case. The guts in here are exactly the same. But here we get the slope at time Tn plus a half, which makes the method implicit. Here we're using a slope at time Tn, which makes it possible to have an explicit method. There's just an extra evaluation of F called for. Okay. Then once we have that, yn plus 1 equals yn plus delta t k2. We only want this. Right. Okay. Both of these methods, the error is order delta t squared. The extra work that we're doing compared to explicit or implicit Euler gives us an extra degree of accuracy. All right. Now, so we're tableau form. It's going to be simpler for the implicit method. So coefficient of K1 is 1. That goes down here. Okay. And then over here, we have multiple of delta t is 1/2. And then A is just a 1 by 1 matrix. We have 1/2 times delta t K1, so we have a 1/2 that goes here. And these are supposed to agree anyway. So that's it. That's the tableau for implicit midpoint. So notice the difference between implicit midpoint and implicit Euler, where those values were equal to 1 in that case. But by using 1/2, that allows introducing symmetry in the error causes cancellation of leading error terms. On the other hand, for explicit midpoint, because we have K1 and K2, we have A is a 2 by 2 matrix. So we don't have K1 here, we only have K2. So coefficients 0 and 1. Our multiples of delta t, look here, we have 0 and then 1/2. And then K1, that's just plain old yn by itself. So we only have zeros here. Everything here is added to 0 anyway. And then over here, we have 1/2 times delta t times K1. And we don't have a K2, so that's 0. So here's the diagonal. The only non-zero entries are below the diagonal, which makes it explicit. Questions about these? All right. Okay, I have 2 more methods I need to show you. Next is explicit trapezoidal. So here we use the slope at time tn and tn plus 1. So there are some similarities here. K1 is the same as in explicit midpoint. And then K2, you look at time tn plus delta t instead of delta t over 2. And then yn plus delta t K1. So this is an approximation of yn plus 1 using explicit Euler. And then, once you have that, then yn plus 1 equals yn plus 1/2 K1 plus K2. So this is somewhat similar to the trapezoidal rule for integration, which is where this method gets its name. Oh, wait, forgot to delta t. So the tableau in this case, we have 1/2 and 1/2, multiples of K1 and K2 in the final formula. Over here we have a multiples of delta t. Well, there's none here, and then 1 here. So then over here we have just plain yn by itself, which is typical for an explicit method, so nothing there. And here we have delta t times K1, so we get a 1 here. There is no K2, so we get a 0 here. And once again, strictly lower triangular matrix, so an explicit method. Okay. Here's something to think about. There is such a thing as an implicit trapezoidal method. I'll write out what the method looks like in another way. So we have f of tn plus 1, yn plus 1. Okay. So that is the implicit trapezoidal method. But how would you go about writing this using this k notation? And then once you figured that out, you could then get the tableau for it. And it turns out to be not too much of a change from this. So something to ponder. Could be a good final question. Questions about any of these? The last method I'll show you is the most popular Runge-Kutta method, fourth order Runge-Kutta method. So okay, all the trapezoidal methods, implicit or explicit, those are also second order accurate. So fourth order Runge-Kutta. Now, there are actually all kinds of Runge-Kutta schemes of different orders. So what I'm showing here is not the only Runge-Kutta scheme that's fourth order, but it's the best known one, and it's explicit.
What's the difference between your stage?
Okay, a stage is referred to really as an evaluation of F. So you could think of it as a measure of efficiency. And yeah, the number of stages is not necessarily equal to the order of accuracy. The order of accuracy is obtained by taking Taylor expansions of all the stages and seeing how many terms you can get to cancel out. So for example, here we have an example of the number of stages being less than the order of accuracy. It's a one stage, second order method. What I'm about to show you is a 4-stage, fourth order method. You do want to try to minimize the number of stages, just for sake of efficiency. But sometimes there are some Runge-Kutta methods that work in pairs. For example, for adaptive time stepping, where the stages in one method might be used in another. So then you're saving some work there. But yeah, there's no hard, fast rule relating the number of stages to the order of accuracy, unfortunately. Okay. But yeah, it can be kind of surprising how sometimes you can get high order of accuracy with surprisingly few stages. Okay. So fourth order, we have K1, K2, K3, K4. So K2 and K3 both use time Tn plus a half. K2 relies on K1. K3 relies on K2. And then K4 uses time Tn plus 1, Yn plus delta T, K3. So then you combine them all. K1 plus 2K2 plus 2K3 plus K4. All right. Now, because these two correspond to the midpoint, time Tn plus a half, a midpoint in time, and so that time has a weight of 4 times the values here and here, it's kind of like Simpson's rule for numerical integration, loosely speaking. Okay. So now we have a 4x4 matrix for a tableau. So can anyone tell me how to fill in the tableau? So, for instance, what do I put down here?
Bottom?
Yes.
1, 6, 1/3, 1/3, 1, 6.
Yeah. So the coefficients of the k's. All right, and then over here on the left.
Zero on the first one.
Mm-hmm.
1/2.
Mm-hmm.
1/2 again.
Mm-hmm.
And then 1.
Yeah. Okay. And now in here we fill in the matrix. So where will entries go?
First one will be 0, 0, 0, 0.
Yep, there's nothing because it's just Yn by itself. Oh, I made a mistake. There, I mean, dealt over 1/2 here and here, and K2 and K3.
The second one, 1/2 of K1.
Mm-hmm.
And 0 for the second 0 for the first one. 1/2 for the second. And 0 the other two. The last one will be 0, 0, 1, 0.
Yep, and since there's nothing on the diagonal or above, that's an explicit method, and that's a tableau. And give it a name, certainly be order errors, order delta t before. Okay. All right. So these are most popular, what are called the one-step methods, that they compute the solution at time Tn plus 1, using only information about the solution from time Tn or later, as opposed to multi-step methods, which use information further back in time. That's what I'm going to talk about on Thursday. Okay. The tableau form it's called a Butcher tableau after John Butcher, who is one of the leading figures in researchers in numerical methods for ODEs. I actually went to a conference in Greece several years ago that was in honor of his birthday. So, so you'll see his name all over the place in terms of developing higher order methods and analyzing them and so forth. And this is a much more concise way of describing a Runge-Kutta method than writing it out in full like this. Okay. Questions about anything? Okay. Until Thursday then.